Let's continue B part 6, exterior algebra. Now, lecture 11, Green theorem in exterior algebra. Now, Green theorem is a powerful formulation of the classical Green theorem using the language of the differential forms and also the exterior derivative. It reveals the deep geometric and topological structure underlying vector calculus. You see, that's analogous, as I said, to the vector calculus, okay, as we derive for the Gauss theorem or divergence theorem. Now, first, classical Green theorem, vector calculus. You see, in the plane R2, for a positively oriented simple curve C enclosing a region D, Green theorem states, see, the integral on this, on C, okay, is a path, is p dx plus q dy. So this integral on the surface, okay, C encloses the surface here, in this case a plane, partial of q respect to x and minus partial of p respect to y, dx dy. Dx dy is the area element, okay, in the xy plane. Now, this relates the line integral around the boundary curve C to a double integral over the region D. You see, this is a classical mechanics, okay? We will apply this to the exterior algebra. Now, item 2, exterior algebra. We recast this using differential forms and exterior derivatives, as we did for the Gauss theorem. Now, let the one form omega p dx plus q dy is called relation 1. Let this to be one form on R2. Then the exterior derivative is a two form d omega, which leads to, you see, d omega, this is a two form. Omega is one form and d increases the form by 1. So this is a two form. That is d applied to p dx plus q dy. Now it's dp dx dq dy. Remember that the dx dy, they are constant, okay? They don't vary with the location. So that's why this differential here reach P and this differential here reach Q. Now, dP, now you see I can express dP as the one form. So this is partial P, partial X dx plus partial P, partial Y dy. And dq is analogous, so partial of q respect to x dx plus partial q respect to y dy. So d omega, I just plug. You see dp here, I plug over here, and this case dq, I plug right there. Now I developed, okay, dx wedge dx dy wedge dx is just this over here. And remember that dx wedge dx is 0, and here I have dy wedge dx is minus dx and dy, because the skew symmetry, you see, I'm just using here. The same in this case. You see, partial q dx dy, partial q respect to y, and this y wedge dy, which also 0, okay? Because it's symmetric. Dx dy, you see, the dx dx, dx dy dy, and so on, this is 0. It's the same, okay, of the classical mechanics, okay? The cross vector between I cross I, there will be 0, J cross J will be 0, K cross K will be 0. It's the same, it's analogous. Now, then I substitute. Remember this minus sign here, okay? This is exactly this minus sign over there. It's written there. So this the omega, the two form is minus partial of p respect to y, dx dy is two form, plus partial q respect to x, dx dy. So I can group dx, derivative of q respect to x, minus partial of p respect to y, dx dy. So you can see clearly that this line integral, okay, on the boundary of the omega is the surface integral, in this case a plane integral of the omega. So that's a green theorem. Now remember dx wedge dy is analogous, okay, to the unit vector k in advanced calculus. So this over here is on the plane in which the x wedge dy, just thinking about the classical mechanics, is the vector, unit vector k. So this plane, you see, that's there. So that's a green theorem. See? If you have some doubt, please, you write down and copy, you see, and check all this derivation over here. You see? That's it.